The nature of light has for a long time been a subject up to debate among scientists. It is considered an electromagnetic wave, but also consists of quantum of energy called photons. It exhibits both wave-like and particle-like behaviors. This is a phenomenon impossible to explain in a classical way, and thus deeply embedded into the foundations of quantum mechanics. In 1801, the physicist Thomas Young succeeded in showing that light behaves as a wave, using the now well-known Young's double-slit experiment. The experiment consisted of passing a beam of light through two thin slits and resulted in measurable interference effects. On a screen some distance from the slits were measured dark and light spots, which respectively correspond to the consequence of destructive and constructive oscillatory interference, which is a wave-exclusive property. If light had behaved like a classical particle, we would see two peak distributions at the positions of the slits, because a regular particle shouldn't be able to go through both slits at the same time. The physicist de Broglie then theorized that matter with energy and momentum could also behave as a wave. When we reproduce the Young's experiment with electrons, it turns out that the same interference pattern shows up, which means that matter can also exhibit wave-like properties. The matter wave can be interpreted as a wave of probability, representing the possible places where an electron might be, and it can interfere just like any other wave. However, the pattern still appears when only one electron is passing through the slits at a time. So we can say that a single electron, in a way, passes through both slits at the same time and interferes with itself before getting to the detector. The pattern then builds up slowly electron by electron, forming an interference pattern, and shows that despite interacting at a point like a particle, the electrons propagate through space like a wave. Similar experiments have been conducted with neutrons, protons, and even helium, and ended up with the same results. We can thus say that light and matter exhibit wave-like properties.
Light can also be considered to consist of tiny packages of energy called photons. Photons carry a fixed amount of energy but have no mass. The energy of a photon depends on its wavelength. Longer wavelength photons have less energy and shorter wavelength photons have more. Energy of a photon is given by Planck constant multiplied by the speed of light divided by the wavelength, known as the Planck relationship. Until about 1900, scientists only understood electromagnetic radiation to be made up of waves. Max Planck and Einstein were studying a phenomenon, now known as the photoelectric effect, where certain types of metal and other materials will eject electrons when light shines on them. They expected that the number of electrons ejected from the metal would increase with the intensity or brightness of the light directed towards the metal. What they found instead was that the wavelength of light was what affected the number of electrons ejected. Only a light above a threshold frequency produced electrons, verifying that a photon transfers all its energy to an electron in the material. The electron is ejected from the material only if this energy exceeds the binding energy. Intensity affects the number of electrons emitted. Compton observed the scattering of X-rays from electrons in a carbon target and found scattered X-rays with a longer wavelength than those incident upon the target. The shift of the wavelength increased with the scattering angle according to the Compton formula displayed. Compton explained and modeled the data by assuming a particle nature for light and applying conservation of energy and conservation of momentum to the collision between the photon and the electron. The scattered photon has a lower energy and therefore a longer wavelength according to the Planck relationship. This helped establish that photons have quantized momentum as well as quantized energy.
Since now we know that the light can behave like a particle and a wave at the same time, now let's check if the classical wave equation can also be applied to the matter wave or not. First, let me introduce you a classical wave equation and the plane wave equation. By inserting the plane wave equation into the classical wave equation, we will end up with omega equal v times absolute k. And from what we learned from quantum mechanics, energy is equal to h bar omega and momentum is equal to h bar k. Therefore, the energy is equal to v times the momentum, which is not the expression we are expecting since the classical physics told us that the energy need to be directly vary with the momentum square. We know that the classical wave equation is not applying for the matter wave, then let's find which one is workable. By considering the relationship between the left and right hand side of the equation, we can see that if you only do the first derivative for the right hand side, the energy will be proportional to the momentum square. So now our new equation will look like this. Then let's check whether this equation is correct or not. By inserting the plane wave equation, it ends up with k squared equal I alpha omega by let alpha equal to m over I h bar and multiplying both sides by h bar square over 2m. What we got is momentum square over 2m is equal to h bar omega. After we prove our new wave equation is correct, then by multiplying both sides by I bar square over 2m and rearrange it, what we got is called the Schrodinger equation. If we insert the plane wave equation into the Schrodinger equation again, the result of equation will look like this, where h bar omega is equal to total energy and h bar square k square over 2m is equal to kinetic energy. So what do we need to do is adding the potential energy term to make this equation complete. Now our new wave equation will look like this, and by changing a into phi sign, this equation will be known as the time dependent Schrodinger equation, or TDSE.